This is Jack Jackson. In this video, we're going to be looking at triple integrals in cylindrical coordinates. Before we get into all of that, let's take a look back at an area of a shape like this. So what we have is we have a circle, and we have the inside of that, a disk, and then we cut out a smaller disk with the same center. Okay, so we're going to center these up at the origin. And we have an inner radius and an outer radius there. The difference in those is delta r. And we cut out of that, we'd have like a washer shape here, annulus of a circle, and we have that area. And then we're going to cut out a wedge of that by intersecting that with this circular sector. So we basically got a circular sector with another sector cut out of it. Now what I want to do is I want to let r be the distance to the midway point halfway between the outer radius and the inner radius. So it's the average radius, r. So that makes the outer radius r plus delta r over 2 and the inner radius r minus delta r over 2. And of course, arc lengths then are just proportional to the angle theta, well, the angle delta theta here. So that's this black length here on the inner one is r minus delta r over 2 times delta theta. And the one on the outside here is r plus delta r over 2 times delta theta. And the red length here, kind of in the middle, is r times delta theta. And this is delta r. It turns out if we multiply this red arc length by this delta r, which is this distance here all the way around here, then we get the area of this piece here. And to show you that, let's look over here. The area we'll call delta A. Well, it's pi big R square minus pi little r square to get the area of the full circular washer. And then it's proportional to the essential angle. The essential angle is delta theta. A full angle all the way around would be 2 pi. So it's the ratio of that central angle to the full circle times that area over here. Well, let's see, we can factor a pi out. And, well, actually the pi's cancel out. That one and that one cancel out. The factor one out here and cancel it. Then the 1/2 I'm just going to bring out front. So then you just have this polynomial squared, this binomial squared here. We got the minus sign. We still got our delta theta at the end. Okay, well, you square this out, you get r squared. You multiply and double it for the middle, you get r times delta r, and you square the last term, you get r squared over 4. Okay, so that was 1/4 delta r squared. When we square this second one out here, we get r squared minus r delta r plus 1/4 delta r squared. And then when we distribute the minus, the first and last terms become negative and the middle term becomes positive. And so the r squares cancel out, the 1/4 delta r squares cancel out, and we're left with r delta r plus another r delta r is 2r delta r. Well, the 2 and the 1/2 cancel, and so the area that you see shaded here has area r times delta theta, where r is the average radius there. So delta A equals r delta theta, and so that means the differential that we have for polar coordinates was dA was r dr d theta. So we've done this before. Now, when we move this to cylindrical coordinates, we're just going to add in a z component. Okay, so again, for double integrals, dA was just dx times dy, or r dr d theta. And if we wanted to do an area, for example, we could just double integral dA, the function 1 times dA, and our differential becomes r dr d theta. And if we had it set up so that the radius r goes from some inner function r1 to some outer radius r2, both as functions of theta, and then we have theta going from a constant theta 1 to constant theta 2, this would be the integral. Notice if we integrate r, we get an antiderivative 1/2 r squared, evaluate it from the outer radius to the inner radius, and we get 1/2 out front, and here we get outer radius square minus inner radius square, both as functions of theta, from theta 1 to theta 2. And that last integral is how we set these up a little bit earlier as a single integral for an area in polar coordinates, an area between two polar curves. Okay, so now let's take this and look at it in 3 dimensions. So if we're talking about cylindrical coordinates, remember we have an x, you don't have x and y and z, you have r, theta, and z. And of course we can find some point here. And we can take a region something like this. This would be analogous to the rectangular prism that we would slice up in the regular rectangular coordinates. Remember, we sliced that up with constant x, constant y, constant z, gave us little rectangular boxes. Here we're going to slice up a region with constant z's, which are horizontal planes here, parallel to the yz planes. That gives us these slices going across this way. And we're going to slice it up with a radial segments going through the origin. So you sort of set your cutter or your knife on the z-axis here and come down, straight down, and then rotate it around and come down and slice it on this slice and this slice and this slice. And then we need a circular cutter, but we cut this with like a cookie cutter or something like that, and we would slice it down in circular manner to get circular cylinder slices coming around this way. So if we take one of those little pieces, it pulls out like this. And so this is our basic setup for one of these little slices. Okay, so now if we look at this piece in a little bit more detail, we can see that, again, r is the average radius between this inner radius and this outer radius. Both of these are circular arcs. This one, this one, this one, and this one are all circular arcs. This is just a cylinder. So any cross-section where we take z as constant has exactly the same area as this base down here. Looks like one of these guys down here, like this, or like one of the shapes here that we just looked at before. So the area there is just going to be r, delta theta. And then we get a volume by multiplying that by delta z. So if we say the delta volume of that piece is r, delta theta, delta z, so the differential then becomes dv, and that is r, dr, d theta, dz. Just to give you a better look at this, I've got a picture here where I can rotate this around. So here you can see the base is a little slice like we had in polar coordinates. Okay, and it's the same straight up and down. So it's the same all the way around that way. These are circular arcs here and here. And that's just a rectangle on the side there. And so you can kind of get an idea of what that looks like. Delta theta is this angle right here. Delta z is the height, this green length. And then r is the blue length out to the middle of this thing. Okay. So there we have that. So what this means is that we can look at writing up integrals in polar coordinates, or actually not just polar coordinates, but actually cylindrical coordinates, three-dimensional. But of course, z is just z in both coordinates, so there's nothing to convert on the z part between the rectangular and the cylindrical. The rest is just like you convert polar coordinates. R is the square root of x squared plus y squared. The tangent of theta is y over x. X is r cosine theta, y is r sine theta. And then the differential dv is dx times dy dz, but it's r times dr d theta dz. And of course, in polar coordinates, dA is dx times dy, which is r dr d theta. So don't forget to put that r in there when you say if you change from dx dy dz to dr d theta dz, you also have to have that factor of r. And then you have to change your limits so that you'll be using these formulas up here to convert. So let's take a look at an example now. Let's set up both the rectangular and cylindrical triple iterated integrals for finding the mass of a region with density given by x plus y plus z. And it's going to be a region in the first octant bounded by the coordinate planes and by the surface z equals 4 minus x squared minus y squared. And we're going to evaluate both these integrals exactly and approximately using a CAS calculator and verify that we get the answers the same. So the first thing we want to do is to be able to visualize what this thing looks like so that we can get some idea of how to set up our limits, both in the x, y, z version and in the r, theta, z version as well. And so here is what the shape turns out to look like. So let me show you this. So here is the graph of this thing in GeoGebra. You can see the shape here. You can see that it's basically in the first octant. X, y, and z are all positive except right on the very bottom here where we get some zeros. And you can kind of see the shape. So the base there is just a quarter of a circular sector. This side is a plane, or part of a plane, with a parabolic top to it and just vertical and horizontal signs on the side. This is basically the same shape here on that side. And then this is our surface here that's our circular paraboloid for the top. So you can kind of get a look at what that shape looks like. And it might be instructive to look at how I actually got GeoGebra to graph this. So what I ended up doing was using parametric surfaces. So I just typed in the algebra view over here, I just typed in surface, and my x is going to be r cosine of t, so it's just t is theta, so r cosine of t, comma, r sine of t for y, so it's just x and y like normal, but just parameterizing them with the r and the theta, or the r and the t. And then the z was 4 minus r squared. Remember, our formula was 4 minus x squared minus y squared. That's 4 minus parentheses x squared plus y squared. X squared plus y squared is r squared. So I see that z is 4 minus r squared. Then I tell it my parameter r is going to run from 0 to 2. Okay, so when you project this thing down on the xy plane, you get a circle here of radius 2 and the inside of that of a quarter of it, right? And so we can see that r is going to run from 0 to 2 and t is going to run from 0 to pi over 2. And then that was the what is that? And then that's the surface. That's the blue surface here at the top. This blue piece. Okay. Now I wanted to also be able to graph the other surfaces here. So here I'll let x be r cosine of t, y be r sine of t, but z be 0. So that's going to be down in the xy plane. Again, I'll let r run from 0 to 2 and t run from 0 to pi over 2. And that's this red surface here, which is the base of this thing. Then this one here, I'll let x be 0. That's going to be on the, let's see, x is 0 is along here. This is the red axis is y. X is the, let's see, wait a minute. Positive. Okay, x is the green one here. X is this one here, red. And y is here. So x equals 0 is going to be along here. Yeah, this purple side is the next one here. So we want to graph that plane there that makes that purple side. And that's this one here, right here. So x is 0, r sine of t is y, and then we want to go up to z equals 4 minus r squared. Again, we use the same limits on r and t, and so that gives us this surface. And then the green one is left. That's this one down here. I guess you could look at the color coding here too to see it. It's a surface where x is r cosine of t, y is 0, and z is 4 minus r squared. And again, same range for r and t, and that gives us this. So that gives us our four surfaces that bound the region. Of course, the domain is all of that plus everything that's inside of that. Okay, and so we can get an idea of what we're looking at. What we're looking at there for our domain. Okay, so now we have to set up our integrals. Okay, so we're gonna set up of course it's just the triple integral over that dv over that domain is the volume, and the triple integral of the delta function x plus y plus z over that domain is the mass. But to actually do that, we need to set that up as iterated integrals. So here's what we end up doing. First, we let z, so if we want to do it xyz version, you start from down here, and the lowest z is always 0. That's just convenient, so your lower limit's 0. And then the top always goes up and hits that surface. So the top z is always 4 minus x squared minus y squared. And so that's going to be the upper limit for my inner integral, which is going to be with respect to z first. Then I must project this down onto the xy plane. We took a look at that a minute ago. And so we get this circular quarter of a circular disc down here. And we see that the x's then run from 0 up to, well, it's just y being the square root of 4 minus x squared, which is the top of this. So if you put 0 equals here, you're going to get x squared plus y squared equals 4, or y squared equals 4 minus x squared. Y is the square root of 4 minus x squared since we're positive y here. And that's going to be the limits on my second part of the integral. And then x's, when you project down on the x-axis, x's run from 0 to 2. So those are limits on the last one. And the function we're integrating is just x plus y plus z. Now, if we want to do that in cylindrical coordinates, then we have to do two things. We have to change this x plus y plus z to cylindrical coordinates. So x has to be replaced by r times cosine of theta, y is replaced by r sine of theta, z is left alone. But then we also have to change our limits. So here we see that the z, again, is going from the 0 up to the top, but the top end is 4 minus r squared, as we discussed a minute ago. And then the r is consistently running from 0 out to a distance of 2. So 0 to 2 for r, and theta is going from 0 to pi over 2. So here are the integrals set up in both coordinate systems. The first one is the original function, x plus y plus z is our delta. This is for the mass. And then we integrate with respect to z. Z runs from 0 to this surface here, 4 minus x squared minus y squared. Then we integrate with respect to y. Y runs from 0 to the square root of 4 minus x squared. And then with respect to x, going from 0 to 2. So there's a rectangular form of it. The polar form, or cylindrical form, is the function is x plus y plus z becomes r cosine theta plus r sine of theta plus z. Your dv, don't forget the r right there. So it's r times dz times dr d theta. So you can't forget that. Well, you can. It's pretty easy to forget that r right there, so be careful of that. Okay, and then the z's run from 0 to 4 minus r squared. The r's run from 0 to 2, and the theta runs from 0 to pi over 2. And I plug those in a CAS calculator, and you can see the details over here on the right. And both of them give me the same form of the answer, which is 8 times parentheses 5 pi plus 16, close parentheses, divide the whole thing by 15. and a per decimal approximation of about 16.91. Now let's see what happens if we try to work these things out individually. I'll start with pretend I don't have a calculator and want to work it out. Could I get this exact value? Well, let's look at the first one here of the integral of x, y, z. Okay. Well, let's look at this right here. There's our integral. We integrate with respect to z. That's not too hard. The x and the y both pick up a z. The z goes up to z squared and multiply by half. Evaluate that from 0 to 4 minus x squared minus y squared. Okay, not too bad. Plug in the z's of 4 minus x squared minus y squared here, here, and here. And then minus, plug in 0 for all the z's. Luckily, this last part's all 0. And then this I just kind of distribute. X times 4 is 4x. Then I get a negative x cubed here. X times this is negative xy squared. Distributed y here, we get the next 3 terms. This one, I have to square this out. Okay, that's a little bit of work. So I needed to multiply this out, say in law multiplication, and then distribute the 1/2. So the 4 times 4 is 16. Half of that's 8. Anyway, I'm gonna leave the details of that for you to work out. But anyway, it's a little messy, but not too bad. And we get these last several terms here, starting with the 1/2. These last 4 terms, 5 terms, starting with the 1/2 x to the 4th, all the way down to the 8. Now we combine some like terms and put some things in order. I put the polynomial in x first. So if you look, there's an x to the 4th term, an x to the 3rd, an x term, and a constant term. Then on the polynomial in y next, there's a y to the 4th and a y cubed, a y squared somewhere. There it is. Then I've got my sort of mixed terms, the x, y squared. Nothing really combines. I just reordered it here. Okay. Now we take an integral with respect to y. Still a polynomial, so it's not too hard to do, but it's getting kind of long. So everything's going to be a partial antiderivative with respect to y. So all of this first part, these 4 terms, just pick up a y as they become like a coefficient, and then times y. So it's like a constant function times y. And then all of these polynomial and y's, you just add 1 to the power, divide by the new power. So that one becomes, instead of y to the 4th, now it's y to the 5th, divided by 5. So it's 1/10 for the coefficient. Y to the 4th, divided by 4. So it's negative 1/4, y to the 4th. That takes care of the next few terms here. And these last terms here, the x's are kind of left alone. But again, the y's, we add to the power 1, and then we divide by the new power. And that's how we get the rest of these. Now we're going to plug in this 4 minus x squared to the 1/2, or the square root of 4 minus x squared, and minus, and then plug in 0. Now when you plug in 0, everything has a y if you look at it for a factor, so all of that becomes 0 for the last part. But now this thing gets to be a bit of a mess. I did combine some like terms here a bit. The stuff that doesn't have the square root, basically, I got that together. So I put this term here with this one here and this one, and got this first term here. And then I took all the ones that had a 4 minus x squared to the 1/2. This term, and I guess that's it. So I've got all of that, which is here. Okay, and then I may be missing something there. And then right here I got 3/2 powers, put those together, 5/2. And then we get, assuming there's no mistakes here, and there may be one, we still get into some a bit of a mess going on to the next part, because some of these integrals here are kind of nasty. They require some trig substitutions and other things. So I'm going to kind of just give up at this point and show you just to point out that this is getting kind of long and messy. But when we go the other direction, it's much better. Now it is still a triple integral, so it's still a pretty long problem, but it's much better than that other one. So here is the way we set it up in the triple integral form. We take the integral with respect to r, both of these, take the integral with respect to z. So the r can be brought out front of that, and out of this I factored an r out, and that picks up a z. This z goes up to square and multiply by half. Plug in the 4 minus r squared and the 0. But there's a z here and this and here as well, so both of those terms go to 0 for the second part. The first part puts a 4 minus r squared here and there as well. I do need to square some of this out and then do some distributing here. So here I square this out and I get 4 squared is 16, half of that is 8, and then times that r is 8r. For the middle term I got minus 2 times 4 times negative r squared is negative 8. R squared, half of that is negative 4r squared. Okay. And if we multiply that by the r up front, that's negative 4r cubed, which is right there. And then I also have an r to the 4th times a half, and times that r is r to the 5th. So it's a half r to the 5th. I put that one up front. Now, what do we get here? Here I'm just distributing this. So I've got a 4 times that r is an r squared term, and I got 4 times this cosine plus sine. So that's this term right here. And here I have that cosine plus sine of theta there, right here, and that's times the minus r squared times that r gives it a minus and then an r to the 4th. So that's this term here. And I put these in decreasing order of r's. It's r to the 5th, r to the 4th, r cubed, r squared, and r. Because this is going to be treated as if it were a polynomial in r, the cosine theta plus sine theta are treated as constants when we do our next antiderivative. So all of these, the power just goes up 1 on r and divide by the new power. Power goes up to 6, makes this 1/12. Here the power goes up to 5, puts this as a negative 1/5 here. Here the power goes up to 4, cancels that 4 down to a negative 1 here. And here that goes up to the 3rd power, that makes this 4/3, and that goes up to the 2nd power, making that a 4. Evaluate from 0 to 2. Once again, they all have an r. R squared, r cubed, r to the 4th, r to the 5th, r to the 6th. Plug in r is 0, they all go to 0. So the second part is just 0. So we just plug in 2. It's nice this time because now this is not a harder formula, it's just a constant. So we can just plug in 2 for all the r's. So all the r parts are just going to become constants. So anyway, we get 2 to the 6th divided by 12 is 16/13. Here we get 2 to the 5th times negative 1/5 is negative 32/5. Here we get 2 to the 4th is 16. 2 to the 3rd times 4/3 is 32/3, and 2 to the square times 4 is 16. I can combine like terms here. 16/3 minus 16 plus 16 is 16/3. The 16's cancel. And then we got a cosine theta plus sine theta, and we're adding negative 32/5 plus 32/3 is 64/15. All right, now I'm going to break this into actually 3 integrals and work out the antiderivative with respect to theta. The constant term just picks up a theta. The antiderivative of cosine theta is sine theta. The antiderivative of sine theta is minus cosine theta. And so we're going to evaluate that from 0 to pi. So we plug in pi, plug in 0. Now let's see what happens. Pi over 2 times 16/3 is 8 pi over 3. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So that term is just 1 times 16. So that's 64/15 there. That term is 0. Sine of 0 is 0. Cosine of 0 is 1. So this is negative 1 times 64/15. So this is, and then we have our minus out here. So it's going to ultimately be plus 64/15. Okay, well, add 64 over 15 plus another 64 over 15, you get 128 over 15. Get a common denominator there of 15, and you get this, which is what the calculator gave us. So that one we were able to track through. Well, it took a little while, but at least it was reasonable to do. Whereas this one over here, at some point, got to be very messy. You might claim it was already a little messy before that, but especially at this point, it's going to get a lot more messy. So it's to your advantage to pick whichever system works out better. Okay, but do remember you have to set up the whatever needs to be changed to the integrand. Your dv has to have an r with the dz, dr, d theta in some order. And then these limits have to be in terms of r and theta and z. If you're going to integrate with respect to z first, these should be functions of r and theta without any z's in them. The second batch should be functions of r with possibly r as a function of theta, no r's in them, but maybe theta's in there. And the last one, if we do theta last, has to be constants there. But because of the way this thing was set up, we were able to have a couple of advantages. One of them was that we ended up having constants for both, not only the last one, which is always a constant, but also for this middle integral we had constant integration. And we also got lucky that all the bottom limits were 0 as well, so that was kind of nice. And so there's an example of a triple integral in cylindrical coordinates.